Alright, so for some of the people, it's not really funny to go through all of that text, right? So I made, basically not me, but ChatGPT gave me the complete visualization for this problem, for this uh, Advent of Code Day 1, Part 1. So this is the dial, the closed dial, which holds 100 kind of positions. And then we can run this to see exactly how the process works, to kind of visually understand everything. So here is the input loaded, everything is here, input is loaded. Then we have speed, we can adjust the speed, we can adjust multiple things, and also we have here step logs in order to debug, to see exactly what's happening here. So and you can see that the starting position is 50. This is exactly the same as I did here, for example, for Kotlin. When we scan in here, initial position is 50. So we're starting from position 50, then we process line by line this input. The input can be found here, but just for it contains a lot of lines, actual input on Advent of Code. But just for simplification, just for running the basic example, I have here the very simplified input, and we kind of step-by-step debug what's going on here. So I adjust the speed, but it doesn't matter as we will use steps. So here in step log, it loads 10 lines of input. And then starting at position 50, we go, and current position is 50, and times landed on 0. This is exactly what we need. As we go through all of the input, this will be incremented. So that's pretty much it. So let's go. So first one is L68. So if a step, so current position 50, but if a step left on 68, then we get 82. That's because here the math is simple. We start at 50, then delta is minus 68, which is, we just need to subtract. When we subtract in this one, then we actually when we subtract in 50 minus 68, we are getting, by math, we are getting minus 18. So minus in 18, if we talk about the plane where we have all of the integers, when we subtracting from 50 to 68, it is minus 18. But we are dealing not with the actually like the line, the like infinite number line. We are dealing with the close ranged. When we get overflow, like when we break the position 0 and going backwards on 18 positions, we subtracting from 100, not from 0. As you can see, like if we had position, we started on 50, it means we somewhere here. When we go backwards, we go backwards all over the 50, and then 18 to compensate the 18 like this, to compensate this additional 18 points from 68. So we land on position 82. Then comes L30. It means that we need to subtract from this one 30. It will land, of course, on 52, somewhere here. So if a step here, we landed on 52. Then write 48. It means we will add, so we will compensate everything that we did and we will land exactly on 0, and this should increment as well. So when we step, that's exactly how it went straight to the 0. So kind of that way, when we process input line by line, we will be landing on different positions, but during the whole experiment, we just count how many times we land on 0 position, and that's exactly the purpose of this advent of code. This is exactly the description, the visual description of this day 1 part 1 problem. So we can just continue with this experiment. So here we last move did R48, then we do L5, which is rotating backwards on 5 positions somewhere here. Okay, somewhere here. So this is 95. And then from that, we need to go right to 60. It's 55. Then step again. We landed on 0. Then L1 is 99, like this. Then left 99. It's exactly, we will be rotating 99 positions backwards, exactly landing on the 0. So this should be also increased, incremented by 1. That's exactly what it did. Then do right 14, and then left 82. So that's the experiment with this input, and the program calculated 3. We landed on 0 3 times. That's exactly the step logs that we see here. So this is kind of visual representation of this task. Using ChatGPT, I generated that one shot, so it's pretty amazing. So hi everyone, this is about advent of code day 1 part 2. At this part, basically, to recall, the first part was when we rotating the dial and we counting on each position it landed. For example, on 20 we do not count, like 90 we do not count, 70 we do not count. We do not count anything other than 0. So what it means is that if you're resetting and running this dial, for example, step, 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 we count exactly when this dial ends on this 0 position. But in day 2, we actually do not need to count on where exactly it is landed. We count how much we intersect this 0 as we are rotating this dial according to instructions depicted in this part 2 advent of code 2025 day 1 part 2. You can see that's exactly what's happening here. So again, we're rotating, for example, rotate left 68. When we, for example, from this one, we can rotate like this, and we should count exactly that this 0 was crossed. This is like the border at which we should not really count. We can't count when we step, when we, for example, from this one we subtract, for example, 15 or 14. So this is position 14, we subtract and end up here. We also count, but also we should count exactly when we cross, when we, for example, do from here minus 15, land up here, but since we crossed, this should increment it, times landed on 0, but here it is actually invalid because this is for part 1, when we exactly need to land on position 0. But here it should be like times crossed 0. And that's pretty much it. But this is really hard work to make this LLMs to understand the requirement and regenerate everything to be precise and accurate. So I skipped that part for part 2, presenting you right the source code, the algorithms that solve this problem. and of course in Kotlin and in Java. And just to compare what we have here. So as in day one, in Kotlin I do reading from file, but in Java it's just from static variable like this. Of course, ideally I should also read from file from Java, but since time does not allow, I show you like that. So the algorithm is the same as in previous in day one part one, except this step. So again, we do an align sequence, map and trim is not empty, and then here flat map on parse individual clicks. So what it means is that we need direction from that file, from this line. Basically, what does that mean is, let me show you again. So here we have input, so we process each time line by line. So in this method that I showed previously, for example, this line is processed. So we have here the first character is R, and then comes 26. So for direction, we just doing text first. First means that we taking the first position from the string, first character, which is R in this case, but it can be L or R in other lines. So if it is left, then -1, right is 1, otherwise is 0, but this will never ever computed because the advent of code does not provide invalid cases. It's always provide either right or left cases. So as we compute direction and amount is that we text drop, we skipping the first part, skipping exactly the direction. Here we skipping, and this expression returns the numeric value that is baked by string itself, like string, okay, the representation, like the number representation baked by type string, but not by the number itself, not by integer. That's why we absolutely need to parse it, and we do this exactly like this, exactly as we did in the advent of code day one part 1. We do the same in advent of code 2025 part day 1 part 2. So basically we convert into int. Here we have amount, and then comes the magic, the Kotlin magic. We have here the generate sequence function available in standard library of Kotlin. What does that mean? In business terms, it generates the such elements. So here we do generate sequence, then there's specifying which elements we should generate. So as you might understand, that this generates a sequence of -1s or 1s, depending on the direction. Is either this -1, 1 or 0, but 0 will not come. So so this sequence will hold, for example, 13 -1s, right? Or for example, for this one, right 24, it will generate exactly 24 ones here. Why? Because we are taking amount. Amount is this part of the line. So generating a sequence, taking amount of this one, and then when we parsed, we kind of of course, when we're doing this, we kind of doing a sequence of strings, right? Sequence of lines, line by line here. Mapping to trim, filter is not empty, then parsing. But here we do need a flat map here, because we are flat mapping to another sequence. If we do map like this, it will return a sequence of sequence, as you can see. Sequence of sequence int. But since we do not need sequence of sequence, here flat map is used to kind of map and flat, get flat and representation of sequence of integers. And then, as you can see, as you understand, the whole expression here, like logically, if we think about this expression, it returns kind of sequence, or Yeah, it's basically the sequence of minus ones or ones. So that's pretty much it. So it will generate a pretty much big sequence, because why? Because we have here a lot of lines of code, like 400 or no, 4,000 lines of code, for which we doing expansion. We kind of expand, for example, R50, right? It will be expanded to 50 elements within the sequence, and for each of these elements we expand in it. So we really need to be cautious about how much memory it will contain. But integers, it's not much. It's for JVM, it's nothing, and for computers, like for example starting from 2019, is absolutely nothing. But if you hold, for example, right, I'm just imagining a situation in production where you hold, for example, some kind of really big object, for example, product of some kind of, I do not know, or sequence of DNAs, right? The sequence of DNA can contain like pretty much a lot of information. So if you're doing like this, we absolutely need to be sure that we are using some kind of iterators or sequences in this case in Kotlin, because lists are eager. If we use list, then we hold the whole memory into the Java memory. But of course, yeah, just thinking about this, and but always we need to profile in order to understand the reality. But for safety measures, if time precious and we understand that this is like expansion, when we do flat map to expand each element into more elements, and so here we understand completely like the expansion is not so big for integers, and since it's integer, it's not a big deal. But if we doing some production job and we don't actually know the input, how much of DNA will it take, right? It's as a safety net. We will just use iterators or sequence, what is available in Kotlin terms. In Java, it is stream. In Scala, iterators. In Rust, also iterator. In Gleam programming language, we also have some kind of iterator available in separate library, not in standard library. So that's pretty much it. So this expression, we can think of expressions, right? Hence the expression-oriented programming, where the functional programming languages, they operate expressions most of the time, not stupid things like statements like most programmers do. So we think more high level and more pleasant to think about programming when we think about expressions. So here, expression, we understand that it returns sequence of minus ones or ones, or alternating sequence, right? The alternating means that sometimes we'll have 10 minus ones, sometimes we'll have 26 ones. So it's alternating, like minus one, then 1, minus 1, and so on and so forth. So that's pretty much it. And since we got a sequence of integers, we are doing exactly the same as we did previously for part 1. We doing scan. So scan function, again, we supply here initial position, which is 50, and then we just supply a rule by which the scan should produce a next position. Okay, we do not do manual work as most programmers do. I mean, I do not do this. Most programmers will write like tons of lots of boilerplate code, 2,500 thousands of Java classes, and some stupid things like that. But actually, I do like this, just on a highest level possible, like in business terms, what we need to achieve, rather than how. So we supplying here the initial position here, and then supplying next position like this, just the rule to compute the next state, given initial or current state, and the next element we computing a next position, next state for this scan function. And the scan function internally does the job for us. It does the looping under the hood. So we do not actually need to think about this. We just think higher level. So, and then we just count in how much it zeros and then just print line. That's pretty much it. Again, pipeline programming, functional programming, data-oriented programming. Everything is clear, everything is high level. No loops, no mutable state, nothing else. And this is the Kotlin code. Then I translated this code into Java. In Java, of course, it's much more not readable because of Java. So the thing is that, yeah, we use the same technique. We use gather. In Kotlin, it's just one line. In Java, we should do like this. Actually, no, sorry. This one is function that we did here, as I did here. Not much of boilerplate from Java here, so it's it's okay. Then filtering for zeros, and just to compare how parse individual clicks look like. Here we in Kotlin return a sequence of integers, but in Java we return a stream of integer. So kind of on the logical sense, sequence and stream are like identical, logically speaking, and identical to what we have in Rust iterators. So in Java you can see it's much more code, and but still it's pretty much okay. So we computing the step count, how many, like here we have amount, but in Java I set like this one, but we can actually do like this. So this is equivalent in Java. Then we parse in the direction, computing the direction. We can actually do like this. So it corresponds 1-to-1. So we compute in direction like this. Again, in Java we do like this char@, 0, meaning that this is the first element. In Kotlin it's much more readable. We just say first element from text from the string. Actually, to make it 1-to-1, I do like this. So direction computed as this one, then step count, how much we should take once or minus once is computed here, step count. So again, in Kotlin it's much more readable. And then for generating sequence, in Kotlin we use this function, but in Java we use int stream generate and then supplying the direction like -1 or 1, and then limit step count. So I think from whoever deals with Java, it's more readable, I think, than in Kotlin generating sequence. But again, for Kotliners, it's much more preferable. But in Java, we do like this. So not much of distinctions, like having the state of the Java today. I do not really see some discrepancies for this problem. Some huge problems from Java, right? The Java evolutions pretty much quickly aligning with other languages, but still we do not have nullable, non-nullable types in Java and other things from Kotlin. So Kotlin is definitely winner, but for this case, for this problem, it's not a much big deal. And again, here presenting the Scala solution. So in Scala, it is like a book, reading the code like a book. Like I absolutely like the Scala way of doing things. So in Kotlin we do everything like that. So it's the same as here. Expression are the same. So this part logically corresponds one-to-one to this Scala. And then we're doing flat map to parse individual clicks, and here we do also the same thing, but in Kotlin. Yeah, and again, in Kotlin we're returning the sequence of integers, but in Scala it is a type iterator, which is trait. Okay, so computing direction like this. So again, I think in Scala it looks much more pleasant to, from the code perspective, it's much more elegant. So in Kotlin we do like this first element, but in Scala we do head. This is the first element from this string, and then matching, pattern matching on L or R the same way is in Kotlin. Then step count also absolutely the same, but in Scala we just do like this, to int without parentheses, but in Kotlin with parentheses. And then for generating sequence we do like this, but in Scala just iterate or fill, step count and direction. So kind of vice versa, right? In Kotlin we do take step count, but in Scala we firstly fill iterator, how much of elements we want, and then the element itself. So fill returns some kind of iterator also, and then doing like this. So I'm not really familiar with Scala yet, just exploring it, but looks absolutely amazing. So the code is really compact, as you can see. In Kotlin we still have like more code than in Scala here. Maybe it can be optimized somehow, but actually it's not the same as in Scala, because in Kotlin we do erroring, but in Scala we do not, so it's not really valid to compare these blocks of code, because they are doing not the same in terms of error handling, in terms of validating the input. But yeah, pretty much cool. And finally, presenting you a Rust version of this algorithm. So on the right it's Scala and translated to Rust. So here again we parsing reading from file. In Scala it's like this one, in Rust it's like this one, and then if something went wrong here, we just supplying the default as a string. Then computing lines, the same as in Scala, lines iterator. Then mapping, streaming, then filter, non-empty. In Scala we directly have on the, I think it's string, we have non-empty on string ops directly, non-empty. But in Rust we should explicitly do lambda with parameter line, and then the lambda body is line is empty not. So kind of in Rust there is a cool part is that we can compute some predicate or some kind of boolean value and then negate it right away, instead of doing like this, because this is kind of hard to read, because we firstly need to understand that we skip this, and then understanding this we compute this is empty or not, and then negating it like this. But if you do like this, then it is crystal clear we computing is empty and then negate it here. So I think it's much more better. So, and then we flat map to parse individual clicks the same way as in Scala. So here it returns an iterator over these items, and in Scala it also called iterator, but of course they are completely different types. In Rust we have iterator like this, in Scala like this. So, but logically, if we abstract away all the languages, in Kotlin we have sequence, in Java we have stream, in Scala we have iterator, and in Rust we have also iterator. The cool part, so this another one mechanism that we can use also probably in JVM languages, but here we're splitting on mid. So this is like index. So we have indexes, right, from 0 up to some point, 0, 1, 2, 3, 4, 5, and so on and so forth. So we're splitting at index 1. What it does, it returns, I don't know how to call this in Rust. I think it's tuple or something like that. But it's like sum type, no, product type containing two strings. And then we can destructure them right away here. In other languages, it's called like destructive assignment, but in Rust, maybe there is another one term, but actually the same thing. So we're splitting right away to direction text and then amount text, then parsing and wrap, so coercing it to use size, and then computing the direction. Direction text is like the first part of the line, as I said. And then here std iterator repeats direction takes step count. We actually can do like this, and then just import from std standard library like this, in order not to specify the fully qualified name of this function. So pretty much the same mechanism. In Scala we do iterator fill step count direction, but in Rust it's much more readable because we kind of from the business perspective understand what it does. We repeating how much time. Actually no, we're repeating the elements themselves, either ones or minus ones in this case. So kind of repeat which element, this element, how many times, this many times. So kind of from the business perspective, I think it's much more readable than in Scala iterator fill and then applying function call, or how to call that. But on the other hand, next position, for example, in Rust, it's not that readable as in Scala, because we care about low-level stuff like whether this is mutable. We borrow in this position, mutable borrowing of this position, and then mutating the state in place here in this function. So that's pretty much it. So Rust being a compiled language, again, it's much more like we can express ourselves in the highest level of abstraction possible with accuracy and with precision. So the language is super good.